Okay, so voltaic cells are spontaneous. Electrolytic cells require a battery. So they're non-spontaneous. So non-spontaneous means what? What's happening?
Requires energy to make the reaction happen.
It's higher than the oxidizing agent.
The reducing agent is higher than the oxidizing agent. Okay, and it does. It requires a battery to supply the energy to make the reaction happen. Okay, so you need to remember spontaneous oxidizing agents are higher than reducing agents. Non-spontaneous reducing agents are higher than oxidizing agents. And if it's non-spontaneous and yet we're trying to get that reaction to happen, we're going to be using an electrolytic cell. It requires a battery. Okay, so we're going to look at the difference between a voltaic and an electrolytic. So if we look at voltaic first, we have our salt bridge, we have our two anodes, we have our solution that contains the electrolytes, and we have to have some way of recording that this reaction is actually happening. So typically in here we'll see a voltmeter. If this is our anode and this is our cathode, which way are the electrons going to flow?
Towards the cathode.
Towards the cathode. Okay. Let's be specific, and we'll. Whoa. Let's be specific and call this zinc and call this copper. So what do we see flowing away from the the zinc anode? In here we're going to see zinc 2 ions flowing away, and in here we're going to see copper 2+ ions going towards the cathode. Okay? In the salt bridge, our cations are going to go this way, and our anions are going to go this way. And we'll call it KNO3. Typically anything with a nitrate ion will work. The anode is which reaction?
Oxidation.
So oxidation reaction, what's happening? Are we gaining or losing electrons?
Losing.
Losing electrons. So we're going to go zinc, solid. It's going to give us zinc 2 plus 2 electrons. So the cathode must be which reaction?
Reduction.
Reduction. So we're going to see a gain of electrons. Okay, reduction reaction.
So is that why the copper 2+ ions go to the cathode to try to stabilize its charge?
Yeah. So our overall redox reaction is going to be zinc solid plus copper ions will give us copper as a metal and zinc ions. That's this side. This is a voltaic cell. If we want to look at an electrolytic cell, we're going to look at the same format. Okay, we still have two beakers. We still have a salt bridge. We still have cathode and anodes. We still have a solution with the electrolytes. Okay, but because this reaction does not want to happen, we're still going to call this one zinc. We're still going to call this one copper. Just to keep everything as similar as we can. So this is a battery. Okay? So if you have the presence of a battery, you're going to have an electrolytic cell. That's one of your first clues when you're looking at a diagram. So an electrolytic cell means that this is non-spontaneous. It means that the reducing agent is greater than the oxidizing agent. So when we look at that, then that means that we're going to call this the anode and this the cathode. So the reducing agent is on the anode side, and the oxidizing agent is on the cathode side. Okay? So we're going to see copper as a solid give us copper ions and 2 electrons. Whereas we're going to see here, we're going to see the zinc ions plus 2 electrons give us zinc as a metal. And our overall reaction is copper as a solid plus zinc 2 plus is going to give us zinc as a solid plus copper 2 plus ions. Okay? So we've kept everything the same with the exception that the anode and cathode titles switch.
Because we need the reducing agent to be larger than the oxidizing agent. And
Exactly.
the reducing agent is always at the anode.
Yes. So,
How could you make sure that happens though? Because if you just switch it up like that, wouldn't it just flow normally, like to be spontaneous?
we're going to do the battery, we're going to supply energy, and so what you're going to see now, we're going to force it to go this way.
Oh.
Okay? Because it wants to go from zinc to copper. It wants to do this. This is the happy reaction, right? But we want it to do this. We want the copper to break down and we want the zinc to build up. So we have to force it to do it that way. So the electrons are still flowing anode to cathode. But here we look at the anode as the zinc, and now we have the anode is the copper.
Yeah.
We're forcing it to go this way when naturally it wants to go the other way.
So then, in the electrolyte solution around the cathode there with zinc, would the zinc ions be flowing into the cathode then?
Yes. Your cations are going to flow this way. Your anions are going to flow this way from your salt bridge. This is still KNO3. And so we're going to see zinc 2 plus, and we're going to see copper 2 plus. Okay? We're just forcing it that way. It doesn't want to do that. Does that make sense?
So then why do the cations go to the cathode though? Does that just happen every time? Like the cation?
Because you have an electron, with your electrons flowing this way, in order for this to stay positive, our cations have to go that way to maintain that.
Okay.
Because we're forcing the electrons to come this way, right? They're going from the anode to the cathode. It's the same here. The electrons are going from the anode to the cathode. So the copper to, like the potassium ions from the salt bridge are going to flow this way because this anode in and of itself is going to end up with a negative charge.
So does that cathode become plated with like whatever the salt bridge is made of? Or
No.
whatever the electrolyte solution?
The electrolyte solution. Because potassium and nitrate are our spectator ions.
Oh, okay.
What's the purpose of forcing it to go the other way? Like, wouldn't it be more efficient?
Say it again.
What's that?
What's going to happen? You use the word plating.
Plating.
But wouldn't that happen like in the
In the
one without a
normal-
battery pack?
Yeah.
No. Plating happens when we put electricity to it.
So those copper 2+ ions that are flowing out of the anion, like does their charge get distributed through the salt bridge then?
No, you would end up with a buildup of copper.
And the
Breakdown.
electrolyte solution?
Yeah.
Okay.
Okay. So cell potentials for an electrolytic cell is calculated the same way. That doesn't change. All voltaic cells, note this, all voltaic cells have a positive cell potential, while all electrolytic cells have a negative cell potential. So in a voltaic, in a voltaic cell equals your E of your cathode minus E of your anode. So when we look at it, our cathode in our voltaic cell is,
Are oxidizing agents
which is your,
larger one in a voltaic cell?
which is copper. So the copper value is 0.34. And our anode is our zinc. And our zinc is negative 0.76 volts. So our overall value for our E cell potential is
1.10.
okay. Over here on an electrolytic cell, you're going to have your E cell, and our cathode is our
See?
zinc, so it stays the same. The formula doesn't change. What the species are for each one does change. So this is negative 0.76 minus 0.34. We get
Negative 1.
negative 1.10 volts. Okay, so the only thing that's changing is what is going where. The formula doesn't change to create that positive or that negative. Okay? Are you good?
Yep.
Wait, Carly, you're good? Cameron, you're good? Alright, so this chart here. Voltaic cell is a spontaneous. It converts chemical to electrical. That's why we can get a reading on the voltmeter. It is a battery. You can create a voltaic cell and it generates electricity, so therefore it is the battery. Anions move to anode and cations move to cathode. Electrons flow into the cathode, oxidation at the anode. It has a more negative electric potential at the anode, strongest reducing agent at the anode. The reduction happens at the cathode. It has a more positive electrical potential at the cathode, strongest oxidizing agent, has a positive cell potential. So when we look here, spontaneous versus non-spontaneous. This one here, electrolytic cell requires a battery. It converts electrical into chemical. Okay, so these three here are what are different. Anions still move to anode, cations still move to cathode, electrons still flow into the cathode, oxidation still happens at the anode. More positive electric potential at the anode, and the strongest reducing agent at the anode. So strongest being in the bracket because now we're forcing it to be that way. Reduction still happens at the cathode. However, now we have a more negative electrical potential, and we're forcing the strongest oxidizing agent at the cathode, and then this is the big difference. Okay? So that's why when you draw your pictures, you need to be paying attention to what you're seeing. If a picture is provided for you, is it a voltaic, like a voltmeter, or is it a battery? Okay? Because that's going to be one of your key clues. Pay attention to your, if they give you redox reactions, pay attention. Are you understanding that it's a reducing agent that is higher than the oxidizing agent? Or is it the other way? One for spontaneous, one for non-spontaneous. Things that you need to look for all the time when you're doing these kinds of questions. So let's work on these questions.